And I am live. That is pretty cool. Today is 2nd of April 2026, Thursday. And let's just like start solving some problems on code forces. Yep, cool. And yesterday was April Fool's Day contest, which was actually crazy. Let me show you the standings. I did one problem. How can Yep. After a lot of tries, I was able to solve one problem. And the reason that I got this repeatedly wrong was this was the problem. We had to spot odd one out. You can pause the video and find out which one it is. And it is C2 because C2 is the only one which appears. This arrow is the only arrow which appears in one direction. Every other arrow like this one has other arrow here, so every other arrow has another arrow in some other cell which is also pointing in the same direction with the same color. So yep, except this one, the arrow in C2, and the answer was actually C2, but C had to be capital, like capital C and 2. That was the correct answer. Shit. And I kept messing it up. Let's actually see. I want to see. Yeah, we will solve some problems, but I want to see what was the answer for some other problems, like problem number B and maybe even D, because my friend was able to do it. Tutorial. What was the answer? B. Okay, they have the direct solution. One usual thing about the statement, a unusual thing about the statement is the presence of an emoji, more precisely a smiling emoji. So okay, let's try to print a smiling emoji. However, the output should be a string of characters and numbers, so we cannot do it directly. There is one more suspicious thing in the statement, the this thing equation. If we should print question mark, what is the meaning of U, capital U plus Unicode? Shade often indicates that a Unicode of a special character is given. Okay, this was like written by AI, like M dash is here. An international standardized encoding for characters, including emojis. A quick Google search can be used to obtain an Unicode of any emoji. For example, this is represented as this. So shit, the answer was 1F601. In hexadecimal, outputting this indeed works. However, there are many possible answers. Shit, so we just... Oh, shit. Okay, shit. We just had to print out the emoji, not the emoji itself, but its Unicode representation. That is something. B.cpp. Yep. And yeah, like my tree sitter is broken somehow. See out, the Unicode for this emoji is 1F601. 1F601. Shit, so I guess this should work for B. Accepted. Like that is crazy. Let's now move on to actual problems, not April Fool's problems. And the next contest is going to be on 7th of April. So that would be cool. 7th of April, Division 2. The length would be 2 hours 15 minutes at the usual time. Okay, let's see this one. Cherry tree. Okay, this one is a pretty cool one. I did read this, but I didn't solve this. Now let's solve this. You are given a rooted tree with n vertices. like N vertices. This is a tree which is rooted and it has n vertices. The vertices of the vertices, because plural, the vertices of the tree are numbered with integers from 1 to n. The root of the tree is number 1, vertex number 1. In each leaf is the last node. In each leaf of the tree there grows one cherry. You want to collect all the cherries, and to do this you perform the following action several times. Choose any vertex of the tree V including the root or leaf and shake it. After that all cherries fall from all the leaves that are descendants of vertex V. If vertex V itself is a leaf, then a cherry falls from it. If cherries have already fallen from a leaf, the tree will break. So such a situation must be avoided. According to an ancient legend, the cherry orchard, the number of vertices you should shake must be a multiple of 3. Is it possible to collect cherries? Now, that is a very cool problem. Uh, just, I don't know why, somehow looks very beautiful. But here, the problem is we have a rooted tree, which can look like anything. And these leaf nodes, these leaf nodes have, let's like forget about the story that they are saying. We just care about the maths in this. So what we have to do is, whenever we have to choose a subset of nodes, a subset of nodes. Yep, we just have to choose a subset of nodes. And let's say we choose this one, and shit, and then let's say this one and this one. So the subset has to be such that all of the leaf nodes are covered as the descendants of those subset of those nodes that we have chosen in the subset. And the size of the subset, there are just two constraints. When we create our subset, the size of the subset has to be a multiple of 3. Remainder with 3 has to be 0, and the leaf nodes of those subsets must cover the leaf nodes of the original tree. Those are the only two constraints. So we just have, and this is not a problem about efficiency, because if we had to find the smallest size of this subset, we could have just chosen the root node, and because that would cover all the new leaf nodes. And if we wanted to find the maximum size of the subset, we would just choose all the leaf nodes. That would be the maximum size of the subset. But we want a size of the subset that is a multiple of 3. That is a multiple of 3. Okay, so we do have a upper limit and a lower limit. The lower limit is 1 and the upper limit is the number of leaf nodes. Let's call that L inclusive. If you have this, can we apply binary search? I guess not, because we are not optimizing for anything. Nope, binary search does not make sense, because in binary search, if your graph is like this, 1 to L, and this is like false and true, then at some point your answer is in one state, and at some point X, your answer switches to the other Boolean state. And what you can find using binary search is this exact point X, where the value of your function switches from whatever it was before to something else. But you cannot do this same binary search here, because if you were to graph this out from 1 to L, false. False means it is not possible to choose a subset of this given size, of some size, and true means it is possible. So we know that 1 is true and L is true, and then the graph is going to be more like this. Some values are going to be true, some values are going to be false. Cool. Maybe then we can have a loop which starts from 1, which starts from 3, uh, then to 6, and keeps going till it is smaller than or equal to L, which is the number of leaf nodes, always having a difference of 3 between the, yeah, having a difference of 3, and then checking if this value, if it is possible to have a subset of size this. I think we can do this. We will start from the leaf, from the root node. Root node is 1, and when we say that we want to increase the size, and the size of the subset, then it means we dissolve this root node, and instead of choosing this, we will choose all of its children, which are in this case 3, this, this, and this, which is actually the right answer in this case. And shit, this process is legit independent. Then let's say, when we have our subset like this, when we only have one node, and we say that the current, that this the current size of this subset is not a multiple of 3, it means we need to choose one node and dissolve it, and instead of having that one node, we can have all of its children, right? So when we, let's say, dissolve this one, we can have, instead we can increase the size by 1, by 1, because like, we already had one here, and if we dissolve this, we will have 2 of its children. So we went from 1 to 2, increasing the size by 1. And this process of dissolving this particular node is independent of dissolving any other node on other branches. Hmm. Hello, guten Morgen, wie geht's? And this is the problem. Let's take the input. No. Uh, okay, we can dissolve these nodes. We can dissolve these nodes. Okay. And it is easier to go from top to bottom. Can we brute force something? No, the answer is no in this particular case. 1 is connected to 2 and to 3. Yes, you could either have 1 or 2 children. It is possible in this case. 1 is connected to 2 3 and 4, you would just choose 2, 3 and 4 as your subset and you are okay. This is unidirectional. Yep, unidirectional. Okay, let's graph this tree to get some idea. This is node number 1. 1 is connected to 2 and to 3, 2 and 3. And then 2 is connected to 4 and 5. 2 is connected to 4 and to 5. 3 is connected to 7 and to 8. 7 and 8. 5 is connected to 6. 8 to 3 and then 8 to 9. 8 is connected to 9. Okay, so we begin here at the root and our size was 1. And we see that this is not a multiple of 3, so we need to dissolve this node. And we get two other nodes. We get 2 and 3 and our size changes from 1 to 2, which is still not a multiple of 3. So we have to now dissolve one of these. But which one do we dissolve? We do not know. We can brute force and try to dissolve all of them one by one. But in this case, we could dissolve 2 or 3 and the answer would be correct, because I think answer would be correct, because let's say we dissolve 2, then we would remove 2 from our set and we would get its children, which is 4 and 5, and the size is 3, which is a multiple of 3, and we are good to go. And same would happen if we were to dissolve 3, we would get its children and we would be cool. If we can afford to brute force, it would be pretty cool. But also, it is not just that we are going to dissolve one of the nodes. It might be that we would like to dissolve all of them or some of them. Yeah. Yep. Brute force is not a choice. Brute force is not a choice because the total number, yeah, because time complexity would be a lot, because at each level, at each layer, this one, this one, this one, this one, uh, there is a possible configuration which is the right one. At each layer there is, let's say the size of this layer is 1, the size of this layer is 2, and by size I mean the number of nodes at that layer, here 3, and total number of subsets for this layer would be 2 power 4, because each node has a possibility of being chosen and not being chosen. Two possibilities multiply by 4 times for 4 nodes. So 2 power 4 here, 2 power 2, 2 power 2 and 2 power 1, and multiply all of them together. That is a very big number. It is essentially 2 power n, the total number of, yeah, because, and 2 power n makes sense because we are trying to choose a subset of nodes and there are n nodes. So 2 power n is the total number of subsets. So okay, brute force is like legit not the right choice. But I think dynamic programming is something we can use here. Since we want three, we want three. 3. I guess we can assign to each node a list of possible remainders of 3 that it could give us. I think that would be cool. That would actually be cool. A list of possible remainders that it could give us. Like for example, with all the leaf nodes, we would say 1 is the only possible remainder of 3 that it could give us. Yep. 1, 1. Shit. Hello. Nope. There is college, but I do not go to my college. Ruin. Shit. Because of this? Yes. I did buy it. And I think it was you who suggested this problem, this specific problem. Prism. 1 here. If we do not dissolve this, we would have 1. And if we do dissolve this, we would have 2. Here also the same, 1 and 2. And this can have all the remainders that this can have. No, 1 is always a possibility for every node, so I guess we don't even have to write it down. For 2 and 3, for 2 and is 0, that is the question. 2 and 0. We should start at the top. And we could either choose this, in which case the number of nodes chosen would be 1, would be the only possibility. And let's say this has 2 children, 2 and 3. If we were to not choose 1 and choose its children instead, we would have 2 here in the list. And what are we showing in the list? I don't exactly know. Z2 has more children, 4 and 5. Increases by 1. 1 2 1 2. 0 we don't know, but 2 is here. And if this has 2 and 1 is always here, all the parents of 2, no, not the other one, but because of 2, 2, 2 means 0. Shared. 2 plus 2 is 0. Like, obviously, 2 plus 2 is 0. Yes, of course. 2 plus 2 is 0. This node, node number 1, has 2 children, 2 and 3. And if this node 2 has 2 more children, then the number of children that 1 had originally, which is 2, we were to split one of those, which is 2, into 2, 4, and 5. Now, the total number of leaf nodes, you could say, is 3. And if we were to take its remainder with 3, it means 0. Therefore, 2 plus 2 is 0. 2 plus 2 is 0. 0, 0 is 0. So we are just looking for a bunch of zeros. Yes, we are just looking for a bunch of zeros or a bunch of things which add up to a number. Okay, this is much better. Or a bunch of things which add up to a number that gives us 0. So every node will also have another key value pair, let's say Z and T, which would be true or false. True or false. This can be very big, 10 power 5. Shit. Any indication what to do? 2 plus 2 is 0. Like, yes, that is a objectively correct statement. But again, how to choose the subset of those nodes? But we are not purely choosing a subset. should we just have to say yes or no? We do not need, want ever to find out anything else. Okay, 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 okay. Okay. DFS, DFS, DFS. Yes, DFS would work here. Yep. Let me write the code and then I will try to explain. ODM. And yep. Vector adj, you could call it. Size would be n plus 1, and vector um, size would be 0, 0. Okay. Yes, this does not make sense. 0, I smaller than n minus 1, I plus plus, L and R, L and R and ADJ, L dot back R and ADJ. Stop the L is invalid. LSP stop blank D. Push back L, right? And we do not see good colors here because the tree sitter is broken. Pair, pair, pair. First means has chosen as a subset with mod 3 equal to 1. Second, mod 3 equal to 0 because 1 is always a possibility. With size mod 3 equal to 2. reference ADJ. Okay. Okay, LSP is not working. That is why we are not getting anything. I would like to have something. Okay. DFS on X with ADJ. Bool. Now if this, we don't even have to do this. We can, I guess, just say auto FNS. Yes. If F, then answer dot first equals to if S. But also a combination. Yes. Yes. And also no, this is not true. Sum equals 0. Okay, essentially the problem has been broken down into, we have a set of numbers. Let's say we have n numbers whose possible values are 0, 1, 2, and we can sort them. We can sort them. We can sort them out. Yes, we can. Yes. Yep, they have a bunch of possible values. All of these n numbers in total, 0, 2, 2, 1, and our goal is to choose for each of these values one of their possible values, so that, or not, yes, choose these values such that the sum could have a remainder with 3 equal to 0, equal to 1, or 2. We have to see what are the possible remainders with 3 that we can get. One is always a possibility. For each of these values, we can always choose 1 as a possible value. We can always choose 1 as a possible value. So that is good. We just have to figure out 0 or 2. Can we get 0 or 2 as a remainder? And we just, okay, we can always, since we can always choose 1, we would choose 1. We would choose only ones from all the values, and then we will see, let's say the sum becomes s and we take a remainder with s. Let's say it turns out to be 1. Now we need to see if 0 is a possibility that we can have, or 2 is a possibility that we can have. For 0, we would like to either increase this sum by 2, so that when we add 2 to this and then take remainder with 3, we get 0, or remove 1 from this. And that would mean when we want to add 2 to this, that would mean change any two of these values from 1 to 2, like increase them. So we just need to see to count how many 2's do we have. If this is at least equal to 2, then we are good. And cool, then we are good. Then we would be able to have 0 as the remainder. And also, since we have two 2's, and when we are also like, yep, or we could decrease the value, that would require at least one count should be at least equal to 1. Okay, 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 okay. T 2 count equals 2 count, and 1 count equals 0. Both are equal to 0. Right, 2 count and 1 count both are equal to 0, and original remainder is adj I dot size remainder with 3, and if f if f, which should be if f, then 0 count plus plus, and if s, then 2 count plus plus. Okay, now, okay, now, what should be the possibilities for this one? Well, possibilities. Shit, I didn't have a timer. My bad. Hello, Kakashi. Yo, this one. Try to do this one. This one is pretty cool. And yesterday's contest was crazy. It was actually crazy. Next time we will get it. Next time we will get it. Yesterday was a new experience. We will get it next time, next year, 1st April. Switch just feels right here. Case 1. Case 1. If ORM is 1, then yes, whatever. If ORM is 1, then to check for 0. If we are now checking for 0. To count greater than equal to 2 or greater than equal to 2. Yes, to count greater than equal to 2 or 0 count greater than equal to 1. If that is the case, then we do answer dot first equals true, or and then if 0 count greater than equal to 2 or 2 count greater than equal to 1, then answer dot second. Or should we first answer, second answer equals answer, and here second answer equals true in case 1. In case 2, and there is also case 0. In case 0, if A is by default true, we need to check for 2. If either this or no shit, 2 count greater than equal to 0 or 1 0 count greater than equal to 1. Okay, case 2, case 2, SA is equal to true, and if 2 count greater than equal to 1 or greater than equal to 2. Okay. And first, second equals DFS on 1 passing ADJ. See out depending on f. Okay, almost done. Let's see. This should work. This should have worked. Shit. Segmentation fault. I guess we messed up with this. No, this is the correct syntax. We can do this. Shout. Hello. How many times do we see hello? We see hello twice. So segmentation fault happened in this part. Nodes are numbered from 1 to 2. Okay, yep. It is happening in the DFS function somewhere. ADGI, that is valid, no problem with that. Or we don't see anything being returned. Auto X in ADJ, C out X. What do we get? 0, 1, 2, 3. Here also, and L is better. Segmentation fault. shit, visit. Ah, shit. Okay, makes so much sense. Vector visited. We need a vector named visited, and after getting n, we will say visited dot sign size n plus 1, and everything is false. And here say visited 1 equals true, and if not visited x, only then visit x. What do we have now? Wrong answer, which is much better than segmentation fault. We have now wrong answer. Okay, this one also says yes. It should not say yes. Yo, it's 3 1 one test case, 3 nodes, 1 connected to 2, 1 connected to 3, 0. Why is this true? No, it should not be. This thing should. It is true because this thing has no child. Yes, makes sense. So if adj I dot size equals 0, then return answer. One test case, 3, 1 connected to 2, 1 connected to 3, and still yes. Not 0, but wait, because it is also connected to the parent. Shit. So size minus 1. One test case, 3 nodes, 1 to 2, 1 to 3, and no. Looks cool. Says no for the first test case, where clearly the answer is yes. Except for 1, do not minus 1. Minus depending on I. If I is 1, then 0, otherwise subtract 1 from everywhere. Cool. Do you need anything else? I guess not. false is okay as the initial value. Yep, if size is 1, this thing does not have any children, then just return. Then we are choosing this, and ORM. ORM ORM is also, original remainder is also correct. Okay. Okay. And the conditions before submitting, let's just check this. ORM is 0. That absolutely means that 0 is a possibility here, and FA equals true. And for SA, to count greater than equal to 2, yes, increase by 2 or decrease by 1 gives the same thing. If 1, then either decrease by 1 or increase by 2 to get to 0, and to get to 2, decrease by 2 or increase by 1. And in case of 2, increase by 1 or decrease by 2. Okay, I guess we are cool. Let's submit cherry tree and see how it goes. Running on test, and this should work, this should work, this should work. Or it just keeps on running. Running on test case 2. Shit. Wrong answer, wrong answer, wrong answer, wrong answer, wrong answer. Wrong answer. We are getting a wrong answer. Wrong answer. Shit. Wrong answer. We are getting. Again, the input part is correct. No problem with that. F. Yes. That is the only thing that we need to look for. F. Maybe we are doing quite a bit of flushing. That is probably not the right, not the thing which is wrong. But the logic seems flawless, so there shouldn't be a problem. Maybe in this part there is a problem. This is here. No, this also seems right. This also seems right. Switch is also right. And then answer is also flawless. Yep, no problem, no problem. Shit, yep, absolutely flawless. I guess we should look at what went wrong. In the second test case, expected no, but found yes. On the second test case, which is this. Okay, let's make its tree. There are 7 nodes. Node number 1 connected to 2 and to 3. Node number 3 is connected to 4 and to 5, and then 1 is also connected to 6 and 7. To count is 1. And the remainder is 1. And to count is 1. But we need two counts. Remainder is 1. Yep, we need greater than equal to 2 counts. So this should not be. Why is it saying yes? Compile, we just have one test case which has 7 nodes, 1 connected to 2, 1 connected to 3, 3 to 5, 3 to 6, 1 to, should I messed up, 3 to 5 and 3 to 4, but okay, 1 to 4 and 1 to, which one is remaining? 7. Why is this thing yes? I equals 1, or see out I space One test case, 7 nodes, 1 to 2, 1 to 3, 3 to 4, 3 to 5, 1 to 6, 1 to 7. Okay, so for 3 we got 1 2, which is correct. 0 1 0 1 for 3, correct, absolutely. But why for 1 are we getting something else? One count, comma, 0 count, not 1 count. Compile. One test case, 7 nodes, 1 to 2, 1 connected to 3, 3 connected to 4, 3 to 5, 1 to shit. One test case. 4 3 5 4 1 6 1 7. Yes, 1 0 count is this and 1 count is this, and the remainder. Then what is ORM? One test case, 7 1 to 2 1 to 3 3 to 4 3 to 5 1 to 6 1 to 7. ORM is also 1. ORM is 1. So we went into this condition, and FA would only be true if either 0 count is greater than equal to 1 or 2 count is greater than equal to 2, which it is not. So we shouldn't be getting FA equal to 2, but we are getting FA equal to 2. For 1, okay, wait, I'll be right back. I have to go to washroom. We'll see. Just 1 minute. For 1, answer first. Why is answer first answer becoming equal to 0, equal to 1? zero count, two count. Two. Wait, this might actually be some precedence thing. Hmm. It is not a precedence thing. Shit. Compile 171 1 2 1 3 3 4 3 5 1 6 1 7. Shit, okay. I do see the problem now. I do see the problem now. If the one viewer who is here, if she can also spot the problem, then they will call me stupid. Shit. We need to have breaks because switch statements are fall through statements. They, as the name suggests, fall through. One test case, 7 nodes, 1, 2, 1, 3, 3, 4, 4, 3, 5, 1, 6, 1, 7. No, which is the correct answer. Shit. So the only problem was switch statement. Shit. If we had used if else, then this would have worked the first time. Okay, maybe not. Shit. What? 23, 23. The logic is correct, and this shouldn't give us a wrong answer. Let's see. We can see the test case like 23 is specifically 1000. And if dt equals 1000 equals reference to print is ambiguous, nope. PP is better because print is also a like thing, an actual thing. If not PP, then keep on going. Else, see out. We need to see the test case. Uh, Test case number 23. Test case number here is 0. Test case number plus plus. Else if test case number equals 23, we would like to print everything. For auto x and adj, yeah, x. Let's see. We should be able to print the solution or the problem. The test case on which we got the wrong answer, which is else if PP is true and n equal to this, then do this. But why are we not seeing the correct output? Do not output this, only output this when PP is false. When PP is true, output this. Mm, 10,000 shared. The test case is this 1, 2, this is a crazy statement. The tree for this thing would look like 1 is just connected to 2, and then 2 is connected to 3, 4, 5. 3, 4, 5. 1, 2, 3, 4, 5. Here the answer is true. Yep. Here the answer is true. Answer is true. What were we getting wrong here? In test case 23, expected is found no. Shit. Why are we outputting no in this case? compile one test case, 5 things. One is connected to 2, 2 is connected to 3, 2 is connected to 4, 2 is connected to 5. Answer is no. Why is the answer no? See out. I space FA SA compile run one test case 5 1 to 2 2 to 3 2 to 4 2 to 5 and no, which means we are exiting before and I is not equal to 1. But this was very stupid. This was also a very stupid bug. Compile run 1 5 1 to 2 2 to 3 2 to 4 2 to 5 and yes, it worked and it should work now for all the test cases hopefully. Yep, probably it is right now. Yep, yep, that is good. Yep. Cool. That was good. And now what do we do after, just after so you solve a problem, what do you do? Like the basic obvious thing is to just delete the whole code and rewrite it again. Int n, take int n, create a vector adjacency matrix which will have n plus 1 things, and those things would be vector of size 0 with integer 0, and then int L and R for int I equals 0, I smaller than n minus 1, n minus 1 I plus plus, C in L and R, and adjacency matrix L dot push back R and adj R dot push back L. Right, we also need a visited matrix with vector visited of type int, and after getting n, visited dot assign size n plus 1, and everything initially is false, and this should be boolean instead of visited 1 equals true, then we will call DFS on this, which will return a pair of boolean values. DFS takes in I and vector int reference adj adjacency matrix and pair response, or answer is false if adj I dot size equals 1, that is this thing is a leaf node and I is not equal to 1. I is not equal to 1. This means this is a leaf node. Then just return the answer, return answer at the end also, return the answer. And yep, good. Then we need two integers, z count equals 0 and 2 count equals 0. Z cnt for number of child nodes giving, number of child nodes giving mod 3 equal to 0 and 2 cnt for mod 3 equal to 2, right? And then for every child of adji, shit, for every child of adji if not visited x, then visited x equals true, and auto const auto or auto const, anything does not matter, f and d equals dfs on x with adj. Okay, and if f, then z cnt plus plus, and if t, then t cnt plus plus. Okay, and rem equals adj I dot size, the number of children, minus, depending on the current node is 1 or not. If I equals 1 question mark, then minus 0, otherwise minus 1 to get the number of children. This thing remainder 3. Now if rem equals 0, then also here auto reference f and s equals answer. If rem equals 0, then f equals true automatically, and if rem is 0, then to get to 2 we need either z cnt greater than equal to 1 or 2 cnt greater than equal to 2. Yep, if that is the case, then s equals true. Else if rem equals 1, if rem equals 1, then if z cnt greater than equal to 1 or t cnt greater than equal to 2, f equals true, and if z cnt greater than equal to 2 or t cnt greater than equal to 1, s equals true, and else if else s equals true right away, but to get to 1 either t cnt greater than equal to 1 or z cnt greater than equal to 2. If that is the case, then f equals true, and then return the answer. Here call dfs f and s equals dfs on 1 with this adjacency matrix C out depending on f. If f is true, then yes, otherwise no. Cool. This does work here. This should work here again, because if it does not, that would be very crazy. We just did this problem. Memory. This is taking quite a lot of memory. Cool. That is done. And cool. We did one problem in 1 hour 30 minutes. That is fine. That is fine. This one was pretty cool. What is the rating for this one? This is F. Problem F in division 3. Problem F in division 3. Editorial. How do we go to the contest itself? Contest 1073, 1072. This one. F. How do we see the rating of this problem? Shit here. 19. Shit. Wait. 1900. That is pretty crazy. Is it 1900? I guess I can go to my submissions and yep, it is 1900. That is cool. That's cool. Yep, and that would be it for today in competitive programming at least. And thank you for being here. Bye.